So the first thing that we do is build a circuit uh, that is based off of the 555 timer, and we looked at the schematic for that diagram a few minutes ago, and I have actually put it together. Uh, I took the 555 timer circuit that I built for experiment 7 part B, and I removed a few components, I removed a few wires, and I was quickly, within about 5 minutes, 10 minutes, I was able to get the project 3 circuit ready. Um, so it's the same circuit that you guys have been looking at in the previous video, in the previous lecture. So in PSpice, I was able to take several voltage sources and put them back to back and generate a bouncy switch. And what I can do in the experiment is kind of use data that looks like a fake bouncy switch. So I'm going to generate a wave by using custom wave gen functionality of the analog discovery. I'm going to take a CSV file, load it into waveforms, and run it through my wave gen into pin 2 of the 555 timer. Uh, so let's quickly. So that's step number 1. So I'm going to hope that when I clean this up, I'm going to get that bounce should be removed by my circuit. So let's start with that. So for this, I'm going to bring up the circuit that I am considering. Let's see, I have this guy right there. I'm going to show you over here. So depending on what your better view is, you can either have the circuit board as your main window, or your the picture, the circuit diagram as your main window. It's up to you. But what I'm going to do quickly is run through the connections on the circuit diagram and compare them to the ones that I made on the circuit board, the proto board. So I have the 555 timer right in the middle over here, and it is still has the notch on the left side, which means I have pin 1 on the bottom left, pin 4 on the bottom right, 5, 6, 7, 8. So all the way to, so I have my 5, 6, 7, 8 going. So 1 through 4, 5 through 8. So that way. Pin number 1 is connected to ground. So I've left that black wire connected to the ground rail at the bottom here. Let's do 4 and 8. 4 and 8 are both connected to high. So 8 goes to high using that red wire there, and 4 goes to high or 5 volts using that purple wire there, and a red wire right at the end there. Pin number 3 is your output, so I've connected a blue wire to pin number 3. I'm going to connect that to channel 2. Let's see, pin number 2 needs to be connected to the switch. Note that when we do the simulation and when we do the fake data, we do not connect the R2 because we need that to go up, down and up. Remember, pin 2 needs to be VCC when the switch is released, and it should go down and then come back up. And I can do that in PSpice, and I can do that in fake data without using the pull-up resistor. I only need to use the pull-up resistor when I actually operate the actual switch. So which is shown to the right here. So that's my actual switch I'm going to debounce. So make a note of that. R2 only when a real switch is used, not the fake switch. So I'm going to use WaveGen to get into pin 2. So let's see. Let's grab a yellow wire so that I can connect my WaveGen, color coordinate things, and go into pin 2. So I've connected that to pin 2 there, and there is a connection to pin 2 that is going to the right here with this orange wire, but I've disconnected it to the second orange wire, and you will see that I will use this to put the real switch in there. So right now I'm not using that because there's a break in that line there for orange. I don't know if you guys can see that very clearly. Uh, So you see that orange wire is now disconnected with that orange wire there. I'm going to later on put a switch in this location. Right now I'm just using fake data. So I have the yellow line going into pin 2. No switch for now. No real switch for now. Okay, what's next? Pin 6 and 7 are connected together. I don't know if it's very clear over here for you to see that there is a connection between pin 6 and 7. There is a resistor there connected to high from pin 6. That's the 100K resistor. That's the brown, black, and yellow. That's 100K connected from pin 6 to 5 volts. Then there's a small little connection over there to connect pin 6 and 7 together. And then from pin 7 to ground using those two yellow wires, I have a 1 microfarad capacitor there. So to zoom out a bit to show you how that is done. So pin 7 is the positive side of this 1 microfarad capacitor. The negative side of that capacitor is connected to that yellow, connected to that yellow to ground terminal there. There is a second yellow wire uh, next to this yellow wire. We are going to use that later on to connect to high. So that's coming up later. We are not using it for the fake data. We are going to use that to place R2 between pin 2 and high. We are going to use that later. Okay, 5 remains as is. So we have 5 through that 0.01 microfarad capacitor going to this end where I have connected that to ground using the two black wires. That remains as is. The green wire is not playing a role over here. That's when we are going to place the switch, because it's going to go orange, 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 green to ground. We are not using that for now. So I hope you guys are okay with all the connections that appear over here. Many things that you might see are sort of a repetition of what you saw in the astable mode of the 555. Okay, so let's bring up waveforms and see if we are able to uh, measure things. Uh, to make sure that I measure both the bounciness or the fake bounced data as well as the clean output, I'm going to place two channels. One channel, say channel 1, I'm going to place that on pin 2, so the same as yellow wire. And I'm going to place, I've connected orange stripe to ground externally, uh, and I'm going to connect the output of the 555 timer pin 3 to channel 2, the blue wire. And blue stripe has been connected to ground externally to keep the number of connections onto the proto board to a limited number. I also need to give it two more things. One is ground and VCC. So bottom rail connected to black, connected to ground of the analog discovery. Top rail connected to red wire, connected to red wire of the analog discovery to give it 5 volts. I believe I've made all the connections here. So let's go ahead and bring up waveforms. Okay. Alright, so that's my waveforms window. Do I need scope? Yes. Do I need wavegen? Yes. Do I need supplies? Yes. So I need those three things. So for supplies, I'm going to set that to 5 volts. I'm going to disable the negative supply. I don't need that. I'm going to leave that on. Okay, so supplies is ready to go. Wavegen. Okay, so for wavegen, I need to import the fake data. So this is how I'm going to do it. I'm going to select a custom option. We have been using the simple one for generating triangle and square and sinusoidal waveforms. I'm going to use custom, and then I'm going to import the data that is uploaded on the class website. So this one is going to be project 3 and fake bounce data right there. So once I do that, it is going to ask me whether I want to change the amplitude and offset and the frequency and the sampling rate of the data that I want to import to uh, waveforms. And based on the experiment write-up, I know that it requires me to go between 0 and 4 volts. So I need to set the offset to 2, and this is given in the project 3 write-up. And also the amplitude to 2. So that way I have the wave gen, the VCC pulse going between 0 and 4. And what else is there? Sampling rate needs to be 4 hertz. So that the entire thing repeats every quarter of a second. So let's see. Once I say okay, I see that. So you see, whatever goes into pin 2 remains high. When you press it, it goes low, glitches because of the bounciness, and then normal state or the released state of the switch is when it is high. So that is exactly the reason why I don't need a pull-up resistor in the fake data experiment. Okay, so what we can do is perhaps make this a bit thicker so that you can take a look at the waveform that we are supplying to pin number 2 of the 555 timer. And once I hit run, it is going to go to running. So it's providing the waveform to pin number 2 now. Let's see. I think I need to turn on supplies. So let's do that. So turn on supplies. Good. Now let's go and take a look at the scope. I need both the channels, one for the input, one for the output of the timer. Let's see if I run it. I think it's going to be very, very fast. Yeah, 1 millisecond per division is too fast. I need to slow things down. So perhaps 100 millisecond is going to be okay. Yeah. So I can see several pulses here. I'm going to remove the noise on both channels. Then I'm going to increase the plot width to 3, and I'm also going to need to adjust the offset so that I can take a look at the entire thing. So I'll change the range to 1 volt per division, and well, I can bring this down perhaps to about 2.5. 2.5 volts is good. Yeah, and if I bring this down as well to negative 2.5, that's good. Uh, okay, so that's essentially how things are getting debounced. As you can see, the yellow wire, which is measuring pin number 2, is has a bounciness to it, but because we have a capacitor of 1 microfarad and resistor of 100 kilo ohms, we are able to retain that high level until that big capacitor reaches 2/3 of 5 voltage. So it's going to be there for longer, and clearly it is more than 100 millisecond here. So when you calculate it out, 1.1 times 100k times 1 microfarad, it should give you what, 110 milliseconds. So there is some leeway over there. So that's your fake data, and clearly it is working because my blue is not bouncy, uh, and um, I think that's about it as far as fake data is concerned. Questions about how we are able to take fake data into the 555 timer to simulate almost replicate a fake switch, and are able to debounce that using hardware which is based off of a 555 timer. Okay, well, if you guys are okay with that, the next thing is going to be to change the fake data to a real switch. So I have a real switch over there right next to the board. I'm going to place that real switch on pin number 2, and I'm also going to place that 100k resistor and pull it up to high. So what I can do here is switch off the supplies, switch off wavegen. Actually, I don't need wavegen anymore, and I can also switch off scope for now. So let's see. I pull out the yellow wire, which is the wavegen. Don't need that anymore. Uh, I am going to pull out the orange wire there. I'm going to leave out the output. The blue wire remains for measuring the output of the timer. I'm going to place the switch. So now what you have is Pin number 2, through that orange wire connected to one end of the switch. The other end of the switch is connected to this orange wire, connected to that orange wire, connected to that green wire, which is eventually connected to ground. Now you might wonder, if he just wanted to connect a switch between pin 2 and ground, why did he have to go through all that? Well, I didn't want wires to cross over and I wanted them to look pretty. That's why I did that. Work around the entire the capacitor here. I also need to place a 100 kilo ohm resistor between pin 2 and high. So I'm going to do that between pin 2 and, so pin 2 is right there. This end, the other end is connected to this yellow wire, which is connected to high right there. So that's how I have pin 2 and the pull-up resistor and the switch incorporated into my circuit. And this is now going to be the real switch, and let us see if we can we are able to debounce this. So what I'm going to do is, I believe everything remains as is. Sure, it is as is. Supplies are going to turn on and scope is going to turn on, and I don't need channel 1 for now. I only need channel 2, and when I move my finger and press that switch, you can see a pulse, and as you can see, the pulse is not very short. It is as long as I wanted it to be. It is essentially at least 110 milliseconds long, and if I hold it longer, it will stay high, but when I release it, if I just press and release it, it is just going to be uh, it is going to be at least 110 milliseconds long. So that's uh, that's going to be well, let me make it a little bit longer so that you can see multiple pulses without. So I've increased the time to 1 second per division, and I'm showing a couple of clean pulses that came through in that 1 second time period for every push. Now, question is this: what if I wanted to make that pulse width longer? What would I have to do? Well, increase the capacitor or increase the resistor or increase both of them. Not this resistor. Actually, this resistor, yes, not the pull-up resistor. You need to increase the time constant of the R1C1. You can increase that by in a few ways. So by doing that, we can increase. So for example, if I replace that with a 10 microfarad capacitor, it's going to stay high for 10 times longer. So that's a quick test of the real switch along with the pull-up resistor incorporated into your circuit. The last thing, and actually the true test of our circuit, is going be to be able to trigger a 4-bit counter that was designed and built in experiment 7 part D. So the goal is, if I took the output of the 555 timer, which is supposedly a clean pulse, and I use that to trigger a counter, my counter should count up by 1 only when I press a button, and it should not count up multiple counts when I press only one time. So that's the real test of my switch debouncer. So for that, what I'm going to do is quickly switch off scope and supplies, and actually you can make you can leave, we don't need the scope anymore. What you can do is, I'm going to take the output of pin 3 and I'm going to provide that as the input to the NOT gate, because we are making that into a positive edge triggered 4-bit counter. The counter is to the right here, which is the outputs of the 4-bit counter control how the LEDs come on and off. So I'm essentially connecting the output of the timer chip, which is pin 3, the clean pulse, to the input of this inverter. It gets flipped, and operates this negative edge triggered flip-flop counter to make this into a positive edge triggered counter based off of the switch. So a few connections to make. I need the power and ground for the counter as well, the board itself. So I'm going to connect the red wire to this supply there, and I'm going to connect the ground to ground here. And I think both my circuits are getting power and ground. Let's see, anything else that needs to be done? I think yeah, we are okay. So let us put this to the test. See what happens here. Supplies need to turn on, and when I turn on the supplies, my 4 LEDs are off right now. Let us see if I press a button, press the switch, they increment by 1 or not. Let's see that. So I pressed it once, you got 1 and 2 and 3 and 4. You see that what happened? It went from 4 to 6 on only pressing once. So it looks like on some of the uh, pushes on the push button, it is going up by 1, but from time to time there will be a state where it will jump up to, like again, it happened again. It jumps up 2. So when it comes to the real test, my circuit is behaving a little bit differently as compared to how I did the fake data. So it looks like my real switch needs a bit longer pulse. So I need to increase either R1 or C1 to incorporate that aspect of the real switch. So what I'm going to do is simply to turn off the supplies again, and I'm going to increase my C1. I'm not going to increase it very slowly. I'm actually going to increase it to a big value. So from 1 microfarad, I will go to 2 microfarad. So I'll double the output pulse duration. And I can do that by simply placing another 1 microfarad capacitor in parallel with the 1 microfarad capacitor that is already present in my circuit. So right now I'm saying that if I have R1 to be 100K, if I have C1 to be 2 microfarad, then my output pulse duration is going to be at least 200, well, not at least, it's going to equal theoretically 220 milliseconds. So it has gone up from 110 to 220 milliseconds. So let's see if I turn on the supplies now, will I be able to count exactly in order or not? So I've turned the supplies on here. Press once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, back to 0. So now it has gone through the exact sequence without any skipping of state, without jumping states. It has gone down slowly. So we have got a very good debouncer circuit working here. However, the problem is this: because we have increased the capacitor a lot, we have essentially assumed that we are not going to press the button uh, between 100 millisecond and 200 millisecond. So we cannot press this increment discounter too fast. That is the problem of getting that hardware debouncer to be very good. So that's a trade-off that you have to make in the design. So we'll talk more about trade-offs, and we'll talk more about how you can improve the energy consumption of the debouncer hardware on Monday. But as far as today is concerned, I think we passed the critical test of the counter being going up only when you push the button and not going up multiple values. Okay, so let's stop the recording and take your